Okay, this lesson is going to start talking about the cofunction relationship between the different trig functions. So let's say that I happen to draw a triangle and a right triangle, as it tends to be. We'll call this angle theta, and here's a right triangle, a right angle. Remember, in trig, in radians, that right angle has a pi over 2 measurement. So if this is a right triangle, let's call this other angle here, we'll call that angle gamma. And that angle gamma has a pi over 2 minus theta relationship, which makes these two angles here, this angle and this angle, they are both be complementary. I want to make sure I get that word right. So this one and this one are complementary angles. Now, what you can notice about the sign of this angle, so if you orient it in a way that this is angle gamma and this is angle theta, the sign of the angle gamma is equal to this side over this side. Well, in the original figure, that is the same as the cosine of theta, which is this over this. So if I kind of label these, let's just call this R, and we'll call this X, and we'll call this Y. In this figure, this is R, X, and Y. Well, it doesn't matter that they're X and Y. The sine of this angle here, this angle gamma, is equal to the vertical over the radius. So what I'm getting at is that the sine of the complement is equal to the cosine of the original. Sine of this angle, which is the same as saying sine of angle gamma, is equal to the cosine of angle theta. So I'm going to sort of erase some of this and show this one more time in a very simple way. Here's an angle, and here is angle theta and angle gamma. And what I really just want you to prove, if I call this C, A, and B, I know that the sine of theta is equal to B over C, but the cosine of gamma is also equal to B over C. This means that the sine of theta has to equal to the cosine of gamma. And since gamma is just the complement of theta, gamma is equal to pi over 2 minus theta. So the same thing can happen here. The cosine of that angle is equal to the sine of theta. That's what makes these two angles cofunctions, or one is sine and the other is cosine. So if you're wondering where the co came from, it came from that. By this logic, I can kind of do this again with some other ones. Let's start with tangent. The tangent of theta would be equal to B over A, but the cotangent of gamma is also equal to B over A. That makes this be true, where the tangent of theta over 2, pi over 2 minus theta is equal to the cotangent of theta, and the cotangent of pi over 2 minus theta is equal to the tangent of theta. So these two are cofunctions. Then the next one here, it's without too much difficulty that we can also show that the secant is equal to the cosecant of theta, and the cosecant of pi over 2 minus theta is equal to the secant of theta. So this is what makes these the cofunction relationship. Okay. These are some trig identities, and identities are things that are always true within a particular domain, and in this case, the domain is theta is all real numbers. So let's keep going. Reciprocal identities. We've already done these. The sine of theta is equal to 1 over the cosecant of theta, and the cosine of theta is 1 over the secant of theta. We know that based on their relationships. We also know that the tangent of theta is equal to 1 over the cotangent of theta. So those are what we call the reciprocal identities. The quotient identities come from the fact that I know that tangent of theta is equal to y over x, which is equal to y over r over x over r, which is equal to sine of theta over the cosine of theta. So tangent is sine over cosine, and cotangent of theta is equal to cosine over sine. Each of these isn't something that I would say you have to memorize so much as you're going to use so frequently that You just need to have them in your head. Another identity that is very common for us is the Pythagorean identity, which for a right triangle in standard position where this is r, x, and y, I know that x squared plus y squared is equal to r squared. If you divide both sides by r squared, you get x over r quantity squared plus y over r quantity squared is equal to 1. Well, x over r is cosine of theta, so cosine of theta squared plus sine of theta squared is also equal to 1. And we actually write it like this. We write it like cosine squared theta plus sine squared theta equals 1. That's the same as taking the cosine of a quantity squared. And that's useful to know that if I ever say the sine cubed theta, what I really mean is the sine of theta quantity cubed. So be aware of that. Also be aware that if I say the sine inverse theta, that is not equal to the sine of theta to the negative 1. So I actually will not use this notation at all because of that complication and that confusion. This identity can actually be very easily manipulated into two others. If I divide both sides by cosine squared, I get 1 plus sine squared theta over cosine squared theta is equal to 1 over the cosine squared theta. And that is 1 plus, this is tangent squared theta is equal to secant squared theta. I know it's going to take a while to get the idea of sine over cosine being tangent and 1 over cosine being secant in your head, but it's really crucial that you do. The other way I do it is if I divide both sides by sine squared. And what I would get is cotangent squared theta plus 1 is equal to cosecant squared theta. These that I'm going to highlight, you really need to have memorized very, very, very well. And if you forget the second two, just memorize the first one and derive the others from that. So you may have done identities before where you transform one side into the other. This is a very simple one where I'm going to put a vertical line and I'm going to work and transform the left side into the right side. So I'm going to do that by replacing one thing at a time. I know that the sine alpha will stay the same, but I'm going to replace the cosecant of alpha with 1 over the sine of alpha. And I get 1. Well, 1 is not equal to the cosine of alpha. So actually, this identity is not true, and that's the only time I will ever do that to you. If I ask you to transform one side into the other, they will be true. So we're going to put a big X through that and say, never again. So let's go to a real one that we might actually see. We're going to use this to transform the left side into the right side. Sorry, I'm actually at a laundromat washing several things, so ignore the sound. But I know I want everything on the left side to be made into cosines. And to do that, I'm going to use this identity and replace sine. Well, I have something that uses sine squared. If I look back up, I know that I have this identity, which can be thought of as 1 minus sine squared theta is equal to cosine squared theta, or 1 minus cosine squared theta is equal to sine squared theta, whichever one we want. The one I want is that first one, or second one. I'm going to replace sine squared, still write the cosine squared, but I'm going to replace sine squared with 1 minus cosine squared theta. Then I distribute the negative and add like terms, and I get 2 cosine squared theta minus 1, and that matches this. As a final example, I could FOIL this left side to get the right side. So cosecant squared theta, because cosecant times cosecant is cosecant squared, minus, you notice they're conjugates, so they're going to be a difference of 2 squares. So cosecant squared minus cotangent squared. Well, let's just use any of the identities we had before. I know that 1 plus cotangent is cosecant. So cosecant is 1 plus cotangent squared theta minus cotangent squared theta. These cancel, and I get 1, and that's equal to 1. Okay, next thing are these applications. Applications problems are exceedingly simple, but you have to draw pictures. So it says, to find the length of Lake Narrow, a surveyor wants to measure the distance between point A and C on opposite shores. So point A and point C, here's our lake. I'm going to put A and C here. They're on opposite shores. From point C, I measure a distance of 250 meters to point B. So that BC is perpendicular to AC. You can see what we're doing. We're drawing a right triangle here. I also find that the measure of angle B in this triangle, so we're going to draw a triangle, is 82 degrees. Can you tell me the distance between A and C, which we've labeled X, to the nearest meter? Well, I know that this distance right here is 250 meters. So what I really have is a right triangle, and I need to create an equation that relates these three quantities. So what you need to be thinking of is, am I going to use sine, cosine, or tangent? The one to use is the one that relates the two sides that are not the radius, not the longest side, and that is tangent. So what I'm going to say is the tangent of 82 degrees is equal to the vertical, which is x, over the horizontal, which is 250. Note a lot of times I talk about vertical and horizontal in a right triangle. I think of this as the radius. I think of the vertical right here as the y and the horizontal as the x. I don't want you using opposite, adjacent, or any of that stuff. It's really not that valuable to think of that. Okay, back to this problem. If I multiply both sides by x, I get x is equal to 250 times the tangent of 82 degrees. So in your calculator, which would be interesting if we can open this within a decent amount of time, I may try to just pause the video and get this open. Okay, here's your calculator. You'll notice at the top it says radians, which is a good default setting, but it's not the setting we want. So I either need to go into the drop-down menu and change the settings on this document to degrees right here, and then I can choose to make that the default if I want. I'm not going to, because I use this calculator in other courses, so I'm just going to hit OK, and at the top it now says it's in degrees. The calculation I want to do in the calculator is the one from the thing. So I want to do 250 times, I go to Trig, tangent of 82, and press enter. And I get this to the nearest meter, so 1779. Let's find this here. Okay, so that's we'll say the about 1779 meters. I'm not going to ask you to put it in complete sentences. So the next one, I want to look at what this kind of refers to here, an angle of depression and an angle of elevation. So this is a person, and this one is looking out and then looks down. So think about it as a motion, and this one looks out and this one looks up. And what's interesting to note, and it took me a while to figure this out, is that they're actually the same angle. An angle of depression is the same by alternating interior angles of parallel lines, yep, geometry, as this angle here, which would be the corresponding angle of depression. And this one here, if that person looked out and up or looked out and down at the same angle, it's the same angle. Or better yet, if I kind of again think about this as alternating interior angles, this angle here and this angle here are the same angle. It's important to know what an angle of depression is not, and it is not that angle. It's not the one between the person and the floor. It's the one between the person's line of sight and the horizontal and then tilting down. So at an altitude of 3,000 feet, the pilot observes the carrier at an angle of depression of 15 degrees. So here's a plane, which I'm sorry, I'm not, yeah, that's a plane, just go with it. And the pilot is at an altitude, so we're going to put an altitude of 3,000 feet, and the pilot looks out to the horizon and then looks down at the ground and sees that that is 15 degrees. And it wants to know the ground distance from the carrier, which is this distance drawn on the ground. So we'll just draw it like that, and we'll call that x. So I have a right triangle, but why don't we just fill in the triangle? I know this is also 15 degrees by alternating interior angles of parallel lines. So if that's also 15 degrees, then I once again can use the tangent of 15 degrees is equal to 3,000 over x. X would be equal to 3,000 over the tangent of 15 degrees, which is about, when you do it in your calculator, 11196 feet. But it wants it to the nearest tenth of a mile. So the problem with that is I really wouldn't want to round this. I would want to keep it in my calculator. So I'm gonna go back over to the calculator, and let's actually keep the value going. So if I want to do a partial value, I'm going to do 3,000 divided by the tangent of 15 degrees, and I get this. Now keep that stored in your calculator, but know that we're going to do a little bit of dimensional analysis. So I can put that that's about 11196 to show my work, but I'm going to want to do 11196 feet times 1 foot, not 1 foot, sorry, 5,280 feet in a mile. Yes, you need to know that. And if you ever want the easy way to know it, as a track runner, you should know that in the old school days, if you look at the legacy record board that we put up, there are 440 yards around a track. 1 mile was exactly 4 laps around the track, so if I multiply it by 4 for the 4 laps, and then by 3 for 3 feet in a yard, I get 5,280. So in any case, when you do this, you also want to do this completely in your calculator so you have the decimal rounding correct. So I'm just going to take this, divide it by 5,280, and you get 2.1 miles. So don't round and then use the rounded figure. Round at the very, very, very end. Sorry, that should say miles. Last problem. The Goodyear blimp is flying at an altitude of 500 feet. So here's the Goodyear blimp. It passes directly, so let's draw the altitude at 500. Passes directly over an observer on the ground. 1 minute later, the angle of elevation to the blimp from the observer. So remember, observer looks out and then looks up. And we're going to assume the observer has, no height because it's just easier that way. That is 24, and it wants the speed of the blimp to the nearest mile per hour. Well, to get the speed of the blimp, I would really just want to know what this distance is here. So again, I can call that x. I can call this 24 if I want to, or I can do the complementary angle and figure out that this thing here is 66 degrees, either way. I'm just going to use the 24. The tangent of 24 degrees is equal to 500 over x, or x is equal to 500 over the tangent of 24, which I'll skip ahead and tell you that that's about 1123 feet. Now again, a little bit of a dimensional analysis. That's 1123 feet, and that is occurring in a time of 1 minute later. So 1 minute, but it wants it in miles per hour, so times 5,280 feet under 1 mile, and times 60 minutes per 1 hour. If you do that all out, you're going to get about 13 miles per hour because it says to the nearest mile per hour. Okay.